All right, so here we go, September 30th, and we are beginning chapter 4. The one thing I do want to point out is that chapter 4 is the very last chapter that we will cover before the midterm exam. And the next thing I would like to point out is that chapter 4 builds builds directly, I will go that far, on what you have done in chapter 3. Okay, so everything that we've done so far, which is equilibrium, which means summation forces in all vector directions equals 0, and summations about any single point equal to 0 for any body to stay at rest, meaning no translation and no rotation. That these conditions have to be met. So in chapters 1 through 3, actually 2 and 3, but we'll go ahead and include this. We did equilibrium in 2 dimensions, and then we extended our discussion of forces and moments to 3 dimensions. And so finally, in chapter 4, we pull these ideas together and we do equilibrium in 3 dimensions, or equilibrium of rigid bodies. And when we say equilibrium of rigid bodies, what we really mean is, if we in the past were talking about static equilibrium in 2 dimensions, we really were talking about a point, okay? Or in other words, we did not take into account the idea that the shape and the size of the object that was being acted upon had a shape. Because, for example, if you have, I don't know why I'm thinking about an elephant today, but if you have an elephant, right, rather than a point, if you pull on the elephant like this, it's going to be different than if you pull on the elephant like this, right? Something is going to move differently. Now, in the case of the elephant, of course, this is not really rigid because he's going to bend his leg. But in any case, if the size and the shape matters, we need to consider (3D) analysis for both forces and moments. So you can probably see I haven't introduced any new concepts here. We've just brought in 2 ideas that we've already been working with. So what this means is, functionally, for there we go, a rigid body to stay in equilibrium, summation of forces in the x direction, the summation of forces in the y direction, and the summation of forces in the z direction all have to sum to 0. And similarly, the moments about any point in the x direction, the moments about any point in the y direction, and the moments about any point in the z direction, I'll have to equal 0. So when we had originally talked about equilibrium of a point, before we learned about things rotating, and before we learned about two-dimensional things, we had two equations for 2D equilibrium. We had summation forces x, summation forces y. And then we introduced a third dimension, and we realized that we also had to take into account the moments. And now that we are going to extrapolate this conversation into 3 dimensions and a body that size and shape matters, we are going to have 6 equations, which also tells us that we can have as many as 6 unknowns and still solve that system. So when you look at your homework assignment for this entire chapter, you will see that you have 1, 2, 3, 4 problems. Okay, 5 problems. 1, 2, 3, 4, 5. Oh, I skipped one, didn't I? Yeah, we have 5 problems. Do you think that's because I'm taking it easy on you guys and because it's going to take you half as much time as a 12 problem set? No, it means that the problems are quite involved and will take you a long time. All right, so if we take a look at the book, we just see what I just wrote out, that in order for equilibrium, we have to set it up so that all of the forces and all of the moments are equal to 0. The next thing that we introduced here, that's a little bit newer, we talked about it a little bit, but not too much. We've talked about supports or connections. And the other piece is that any structure that is being anchored or sits upon a surface or is tethered in any way, there are going to be reactive forces that are brought about just by the object existing in 3-dimensional space. For example, the tables here, they have legs, and whatever the weight of the table, that weight has to be completely borne on the legs. So that means that the reaction forces act upward if the force is straight downward. And the distribution of that weight, the force in each leg, can be equal if the weight is equally distributed, or if we place a weight really heavily right here, this leg is going to bear more than the other 3 legs. And using summation of forces, summation of moments in any 3 directions, in all 3 coordinate directions, we can determine what those are. But this little diagram gives you an idea of the type of support, the type of, reactions that different supports will provide. So if you look at any sort of a roller or a rocker or a bar sitting on a frictionless surface, the only sort of reactive force is going to be something that is perpendicular to the surface of contact between those 2 things. If you think about it, a roller, like this chair, how handy we have furniture, I can push on it with almost nothing in this direction, I can move, because it will not bear a force in the x direction. The only kind of force it bears is straight down. Now, if I push on it too far, hard, it's going to tip. But that has to do with some other issues as well. But so these will tell you what kind of reactive forces you draw in your free body diagram. Now, if you have a bar like this that is not sitting on a frictionless surface, but rather is sitting on a rough surface, it can bear a force in either direction. Now, the actual force is going to have a direction something like this, but it's a lot easier executionally to draw the force as having an x component and a y component and possibly a z component. All right, so if you draw it at an angle, it just because you're going to have to resolve it, so you might as well just start by calling it out in coordinate directions. All right, here is an interesting thing that will come up a lot. We're going to actually do these toward the end of this course, maybe chapter 6, 7, 8, I can't remember. And then later when we study mechanics and materials, we'll do this a lot as well. But this is a little bit of a truss, and a truss is just a structure that's designed to distribute weight. So you've seen trusses like on bridges. Okay, a bridge truss is designed so that you have the span of a bridge and the weight of cars and people walking across that bridge act downward, but the truss distributes the weight so that it's not all borne on a center piece. And it does that by having reactions at A and B, and then you have some applied loads here. But basically, if you look at the way that they write out the reactions at A and B, A, which just looks like a little triangle, is called a fixed support. B is on rollers, or it's a rolling support or a free support. So A has both X and Y components, but B just has a Y component because B doesn't allow for, it doesn't anchor it in the X direction. Now, the reason for that practically is anything like a bridge, if you think about how a bridge works, a bridge will tend to be spanned upward, first of all. You know, when it's not loaded, it'll be like in an arch. Then it pushes down. What happens to its horizontal length when that happens? Yeah, it expands. And so if you anchor up both sides, if you have a fixed support on both sides, it's not going to be able to move in response to that load. Also, cold and hot expansion, and just other things that happen with materials. I have some pictures, they're on my mechanics materials page, but the Willwood Bridge, which is southwest of here, actually is a really good picture because there are expansion joints in it. So it's not just at the end where all of that is taken up, but there's like, I like to think of them as cracks in the sidewalk where it's a little bit more complicated than that, but that allows that bridge, sections of bridge, to expand and contract. And that's actually why aside from the pour, that's also another reason why there are expansion joints in a sidewalk, why there are cracks in a sidewalk, so that the concrete can expand and contract a little bit, mostly with weather, a little bit with load, but mostly with weather. All right, so when you're working problems like this, they start, the authors work on two kinds of problems. The first thing that they do is they ask you to take a look at problems that are two-dimensional, where you have to compute the reaction loads. And then you do summation forces X, summation forces Y, summation moment Z, right? Like this. Sample problem 4.1. We have this kind of a crane bearing a weight anchored into the wall. Now, the way that this is drawn, A is a pin, which will bear an X and a Y force. B will only bear an X directional force because it shows it as a non-fixed support. So those are the first things that you need to draw. The other thing I would strongly suggest to you, like if you think about the reaction force at B, you know that B is going to be pushing out on this crane. You could also probably suppose that A is pulling the crane back into the wall. So you might see that this is drawn incorrectly. I would recommend that you always draw your reactive forces as positive, because otherwise, if you get a negative of a negative, that means it's really positive. If you always draw them as positive and then do your math as though they're positive, if they are in fact negative, it will come out a single time in the math and you won't be confused by what does a double negative mean, or just forget it and put it in incorrectly. So you don't have to follow that. Once in a while, I'll have a reason not to, but overall, I do exactly what the authors have done here, which is draw all of my reactive forces positive, and then I stick with that as I'm doing my free body diagram and my analysis. And then if it comes out negative in the answer, I then switch it. But the whole time that it's working, the whole time I'm working the problem, I don't switch it, even when I know that I have drawn it incorrectly. It's just a technique for solving. All right, so moving forward, let's take a look at one of these fun ones. Okay. Problem 4.F.1. This is just a free body practice, but we'll take a look at this. We have two crates in the bed of a pickup, and we have a point G, which is the center of gravity. This becomes really important on things that rotate and things that tip, okay? But in a pickup like this, the center of gravity will tend to be forward, and that's the center of gravity of the pickup, not as it's loaded. But the engine of this pickup is in the front, so the center of gravity or the balance point for this pickup is more likely to be closer to the front than it is to the back. All right. And that's kind of what they're getting at here. But that is the point from which we can assume the entire weight of the pickup acts for purposes of analysis. So we have two crates, each with this, placed as shown in the bed of a 1,400 kilogram pickup. Draw the free body diagram needed to determine the reaction of each of the two rear wheels at A and front wheels at B. All right. Well, let's draw a free body diagram. The first thing I'm going to do is to draw the truck like this. Not very artistic, but definitely gets the point across. Crate C is a weight, so it's pulling down. That would be the weight of C. D is also a crate, which pulls down with the weight of D. G pulls down with the weight of the truck. And then A, which is the rear wheels, reaction at A, pushes up. And B, the reaction at B, pushes up as well. All right, now we're not quite done yet, but I want to note the way I have this drawn, the reaction at B calculated here is the reaction load on two tires. That means, or therefore, the reaction at B on one tire is equal to 1/2 the R sub B calculated in this picture. And similarly for the reaction at A, right? There's no point in writing two of them here. We're assuming that everything's equally distributed. In other words, that crate is sitting in the middle of the bed, both crates, and that they're loaded relatively evenly, and also that the weight of the engine is equally distributed out of the page and into the page, okay? Otherwise, one set of wheels might be bearing more load than the other. All right, so in addition to my free body diagram, I need to do, in addition to my weights on my free body diagram, I need to dimension these because I'm going to have to do not only summation of moments, summation of forces, but summation of moments. And I don't only need to know the dimensions of the pickup from the back to the front. I'm also going to need to know the dimensions. Let's see, G is right here, between the different loads. So the distance from the back tire to G is 1.8 meters. And the dimension from G to B is 1.2 meters. And the dimension from the front wheel to the front of the pickup is 0.75 meters. Okay. So the next thing I need to do is to make a determination about what the distance is between these loads based on these dimensions. Well, to find the distance between the crate and the rear wheel, I can see that the length of the pickup is 2.8 plus 1.7 meters, which is 4.5 meters. And I can see that this dimension from the rear wheel to the front is 1.8 plus 1.2 plus 0.75, which is 3.75 meters, which means that this distance to this distance is going to be the difference between these two, or 4.5 minus 3.75, or 0.75 meters. Okay. I also need to determine the distance between R sub A and the crate. Okay, so I know this is 1.75 meters. I know that, or this is 1.7 meters. Sorry, this is 0.75 meters. So this distance must be 1.7 minus 0.75, which is 0.95 meters. And then this distance is 1.8. This distance is 0.95. So this distance between W, D, and G is going to be 1.8 minus 0.95, which is 0.85 meters, I think. 1.8 minus 0.95. Yeah, 0.85 meters. And then I've given this distance, which is 1.2 meters. All right, that's a complete free body diagram of that truck. But now what I can do, I could go ahead and finish this problem. I'm not going to go, you could say summation forces, all the forces are Y equals 0. And then the summation of moments about any given point also have to equal 0. So I know the weight of the crate, which is 350 kilograms times 9.81 to get it into newtons. Similarly here, the weight, the mass of the truck is 1,400 kilograms. So if I multiply that by 9.81, that would be however many newtons it is. And then what I have is two unknowns. I have the reactions at A as an unknown, the reactions at B as an unknown. I also have two equations, okay? So just from an execution point of view, summation forces, I would just add everything. I would just say the weight R of A plus R of B minus WC minus WD minus G equals 0. To do the summation of moments, remember a moment is a force times a distance. So if I choose one of my unknowns as the point I'm taking the moments about, I will eliminate one of them from that equation because anything times 0 is 0. So I would probably take the moments about either point A or about point B. It'll still work if you choose any other point, but if you choose one of those, one of the unknowns will go away and you can solve the moment equation directly. So let's say here, choose summation moments about A equals 0. And then the way that you can compute this is, remember this from the right-hand rule, a counterclockwise moment is positive and a clockwise moment is negative. So if you think about putting a pin here, this is my pivot point. W sub C will make a counterclockwise moment, so that's going to be positive. So if I take this distance, that's going to be 0.75. WD is the other way, it's clockwise, so it's going to be negative or clockwise. This moment arm is 0.95 meters. G, similarly, is clockwise, so negative. And so that distance is going to be 0.95 plus 0.85, which is 1.8 meters. And then last but not least, R sub B, think about a pin there. This is going to create a counterclockwise moment, so that's positive. So R sub B times this moment arm, which is 1.823 meters, equals 0. All right, so we do not know this, but we know this. It's 1,400 times 9.81. We know this, 350 times 9.81. We know this, 350 times 9.81. So that means that we can use this equation and solve directly for R sub B, right? And then we can do the same thing up here, where we just say, by the signs, down is negative WC plus R sub A minus WD minus G plus R sub B equals 0. I find R sub B here, plug it in here, solve for R sub A. And then I have R sub B that I calculate is some number in newtons. R sub A is some number I calculate also in newtons. Oops. And then recognizing that I have two wheels in the front, two wheels in the back, I would divide it to get the reactive force on each wheel. You guys have questions?
That way of direction.
Sorry? Oh, it's gonna be in the Z direction, right? Because remember using the right hand rule once again, the force is purely Y, the moment arm is purely X. So it's either gonna be into the board, which would be negative Z, or out of the board, which would be positive Z.
Yeah, first of all, we're multiplying by 0.75 SW, which weight,
Weight of the crate at C. Times the distance between, I decided to take the moments about point A. So this is the distance between C and A. So all of those distances would be distances between that load and point A. Yeah. Good question. What else? What other questions? All right. So I think I don't really have time to set up a fully three-dimensional problem. There are some in the recorded lectures, and I'll put some up in the PowerPoints. But I just want to show you some other, this page in your textbook 209 and the edition I'm using shows you some other reactives. If you have a ball, like on these little chairs, this chair is free to move in the plane of the floor, whatever you call that, X and Z. So the reactions in the X and Z direction are equal to 0. A ball only supports that perpendicular force, okay? A roller, on the other hand, would be locked in one position. So it may not do one in this direction, but it wouldn't move in this direction and also in that direction. Rough surface ball and socket are the same. And then we got these universals. I've never really given students a problem with the universal joint because they're a little freaky. They just take a long, long time. But basically it supports forces and moments. So there can be reactive moments at a universal joint as well. And then a pin and bracket. So yeah, I will not subject you to that, just so that you know they exist in this world. All right. What's that? Yeah, just to let you know how much fun, how much fun it can be. All right. So the next thing I want to show you is just something that your authors started the analysis for. This frame is a three-dimensional pipe. So it comes straight up out of the ground, then goes over, and then even though it's not really that clear, goes straight back. So this thing, if you looked at the top of it, would just look like this. Like here, it would be going straight down, and it would look like that, wouldn't it? So everything's a 90-degree angle, even though in the drawing, this looks like it's different than 90, but that's just because of the perspective. All right. So what we have a tether between point E and G, which is shown right here. We have a ball and socket at A. So those are those reactions. And once again, I want to point out positive, 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 right? The weight pulls straight down. And then here at D, we have a fixed support, positive, positive, positive. Okay, so that means the way that this is drawn, we have 3. This is going to have 2 components, right? 4, 5, 6, 7, 8, 9 unknowns, essentially. So something's got to give. If they don't give you some of them, we cannot solve for 9 unknowns with 6 equations. So they'll give you some information in here, but basically, you can't really do anything with reactive forces. You just have to leave them as those unknowns unless they give you a number. Sometimes they'll say the Y component of the reaction at A is some number, but if they don't, you just have to leave them as variables. Then you break them down into unit vectors, forces, all of this is the way that you've worked it before. Okay. And then my advice to you, if you are working a problem like this, is to go ahead and to do the long work of to set up all the forces X, all the forces Y, all the forces Z, and choose a point to take the moment about that has a lot of stuff you don't know. So you might choose point D, because then you're not going to have moments from any of the reactive forces at D, or choose A. It's totally up to you, but I would choose one or the other of those. Then you're going to have the moment that T causes about this, which you can do using the determinant, right? Because you can write T as a vector and you can write R as a vector. R would just be from here to here. So 1.12 or 12 feet in the Y direction and 6 feet. So it'd be 6I plus 12J to get to here. And then the weight, 12I and 12I and 12J. And then D is going to have 3 components. You can set those up as determinants, right? Now, when you do that, you're going to come out with moments that have I, J, and K. And then you can pull together the I pieces of the moments, the J pieces of the moments, and the K pieces of the moments. But I'll tell you right off the bat, if you have more than 6 unknowns, you're not going to come out with numbers. So I have to give you enough. But you can always set that up. The next piece of advice I would give you when you attack these problems, a lot of people are way more comfortable with the force equations. So they'll try to run the force equations first. And just as often, one of the moment equations will pop something out quicker. So after you set up all the equations, all 6 of them, just give yourself a minute and take a look at the problem. And when you do that, it's likely or possible that maybe one of those equations only has 1 unknown, or 2 of those equations share 2 unknowns. And you can solve that a lot easier. Or you can do it in Excel, or you can do it in a problem solver. All right. All right, so you have any questions about that? All right, so the first problem, we're gonna have a short lecture today, and then I'm gonna take a look at my grade book and make sure I haven't done anything. The first problem that you have is 424, which I think is a 2D problem. What's up? Oh, 4.2, that's so easy. Yeah, got a gardener. There you go. Gardener, wheelbarrow. The wheel will only have a single reactive force acting up because it will roll in the X direction. 4.4, beam loading shown. The reaction at A, this is a pin. So you're going to have X and Y possible. And then the tension in cable BC, you can just think of that as being a down arrow and just use this rod as being the free body diagram. In other words, you don't really even have to think about the reaction at C. Okay. So there's 4.2, 4.36. Here, yeah, same sort of a thing. Here you have, this is a sliding support, so this is only going to bear in the Y direction, right? Or excuse me, it's not going to bear in the Y direction. So all you have is that perpendicular contact, and then you have 2 cables. You have this 20 times 9.81, and then whatever this is.
Why is that very nice version?
Well, it's actually going to bear, now that I look at it, it's going to bear like that. It's perpendicular to that surface of contact. So you are going to have a reaction at A and a reaction at A, X, and a reaction at Y, okay? So in other words, it's going to bear perpendicularly to the surface of contact. And you could break that into an angle, but my advice to you would be to resolve that into the reaction at D in the Y direction. I know it's pushing that way, but I'm just going to call it positive, like that. And then the same thing here. Reaction at A in the X direction, and reaction at A in the Y direction.
Isn't it a frictionless?
Sorry?
It's a frictionless wall, right?
Oh, is it frictionless? See,
So it wouldn't
Yeah.
know why.
right. Yeah, if it's frictionless, it's just gonna be X. Yeah, see? I was just saying, you're gonna end up with way too many. I couldn't see how to solve that unless they gave you some more information, but they do because it's frictionless. So that means that that surface of contact going back to our like that. Yeah. So. All right, and then where do we get, I think you only have two, 108 and 132, I think are three-dimensional problems. 108. Yeah. Now 108 is three-dimensional. So it's the same thing, but each of these, you have a reaction. Now, if you think about it, the bar is being pulled on by these forces. You can think about the tensions just in those two cables, but here at A, that's a fixed support. So you're gonna have a reaction at A in the Y, reaction at A in the Z, out like that, and reaction at A in the X, okay? Mhm. That's gonna take, that will take you a while. And then 132, let's see. Yeah. 132, we have a bar. It's not straight on with the X-axis. It cants out of the page in the Z direction. So once again, this is going to be a fixed support, so it will bear all three directions. B, let's read it so that I don't support a ball and socket attached, frictionless, once again. So, yeah, so there you go.
A to G, real fast right there.
The vector, A to G, absolutely. Let's take a look. I'll just try to do it right here. All right, so what I would do is do A to B, all right, to start with. And then it says that G is at the midpoint. So if you find the length of this, A to G is 1/2 the length of A to B. And it'll turn out that all the dimensions will actually be half as well. So in other words, if you go A to B, and you can say, okay, let's do vector AB. From A to B, in the X direction, we go -600 millimeters. I'm going to say 0.6 meters, right? Then it goes up 0.4 meters. And then it cants out of the page, which is positive 0.15 meters. Since AG, because G is at the midpoint, is going to be -0.3 meters plus 0.2 meters plus 0.075 meters. Okay, or you could find the angle and do that as well. You could find the angle and then do the directional cosines. And if it wasn't at the midpoint, you'd really kind of have to. So, but the fact that it's at the midpoint will allow you to do that. Okay. All right, that should be fun. So now you know what you're doing for the rest of the week, right? Yes. Well, I am not going anywhere. So if you need my help, I will be in my office. I'm going to go ahead and stop the recording.